today, so yesterday in discussion section, you did some 1D problems. Hopefully everybody got through the first one as intended and actually were able to work a little bit on the more complicated one. Very similar to this one, only everybody was falling. In this case, everybody is jumping. And we started going over this, but let's review some of the highlights. The first thing is that this is a problem where the question is related to the top of the jump. So can someone remind me what it means to be at the top of our motion if we're jumping or moving through space? Yes? Velocity is 0.
Meters per second.
Meters per second. In what direction? Is it your total velocity? Or only the vertical component? Who votes total? Who votes vertical component? Look at that. We can even do the old-fashioned non-clicker way. Excellent. Yes, this is the vertical component only. Now, in this particular case, we're only moving vertically, so it is the total. But in general, it's the vertical component of the velocity. The other thing is to find what the real question is, and the question is, how long is the delay? And that, again, you see a problem with this many words, it's very easy to forget what the question is, and that's why we have the find box in the solution. So it really focuses your attention on what is it we're going to want to answer as a question. Now, the other feature is we have all our given information that we have to sort through. Where the ball is, its initial speed, the player jumps with an initial speed, and where the player is. And a question I got asked the other day after class is relevant to this. If my person is standing here on the ground, not moving and not doing anything, what is their acceleration right now? 0. Their acceleration is actually 0. There's still gravity. We just haven't learned the other part yet, that there's also forces from the floor. And this is one of the challenges with physics at times, is I can't teach you everything all at once. We have to learn it in some sort of order. So when we say that an object always experiences an acceleration of 9.8 meters per second squared down, the key part that I didn't really emphasize well on Wednesday, you keep in mind, this is what we call in free fall. We sort of implied it when I did the comparison of the paper and the keys, right? We said we ignore what? Air resistance, which is another force. Anytime you're interacting with something, so if I'm holding a rope and swinging through the air, is my acceleration going to be 9.8 meters per second squared down? Probably not, because I'm holding a rope. If I have a parachute, is my acceleration going to be 9.8 meters per second squared down? Probably not, because I have a parachute. So in the problem you did yesterday, or set up the second problem, the person you were trying to save that fell had a different acceleration than 9.8 meters per second squared, because we did not ignore air resistance for them. So I had to give it to you. So there will, like I said, be those cases. For this person, when I jump, when do I have an acceleration of 9.8 meters per second squared? Right? So if I'm going to jump, at what point do I get an acceleration of 9.8 meters per second squared down? Oh, let's make that a clicker question. So when I jump, when is my acceleration 9.8 meters per second squared down. Some possible answers I heard out there. As soon as I leave the ground, after I am in the air for some time, which you'd have to solve for presumably, so you do a quick little calculation to figure out when you start accelerating downward. On my way up only, on my way down only. And as soon as I leave the ground, and we'll add to this just the whole time while in the air, so both up and down and all of that. So what do you think it is, A, B, C, or D? Excellent. Most people went with as soon as I leave the ground. Keep in mind, the acceleration due to gravity doesn't care whether you're moving up or down. It's always down, and it's 9.8 meters per second squared. Why is that? Because when I'm going up, it's slowing me down. When I'm going down, it's speeding me up. And it's always there. So it's always 9.8 meters per second squared, and it always points down. And it happens as soon as I leave the ground. Any questions on that part? Yeah.
What about the acceleration from your legs?
Excellent. So the acceleration from your legs pushing you up is all built into my V naught, right? The speed, it says in the problem, 3.5 meters per second, right? So I leave the ground with a speed of 3.5 meters per second. So I went from V equals 0 to V naught equals 3.5 meters per second. Presumably in some time, the time it takes for me to jump, maybe takes, I don't know, 0.1 second to jump. So I had an average acceleration of delta V over delta T during my jump. As soon as I leave the ground, I'm not jumping anymore. I have no acceleration from my jump. I just have acceleration from gravity. And that's my 9.8 meters per second squared down. And this is where, again, I've made the comment before, the challenge between intuition and why people think physics problems, they don't look quite real because they don't really quite know how to connect. You know, we make reasonable sort of breaking the problem into pieces. There's my jumping, and we'll do some problems with jumping later on when we learn about forces. What's the force of your jump and so on, where you have to worry about that. Right now, we're just worried about you get up to some speed by jumping and then you leave the ground. And all you need is the V naught and what happens after you leave the ground. We're going to be launching cannons, we're going to be throwing cars around, we're going to be launching catapults, and all we're going to worry about is something happens to get it to an initial speed and then gravity takes over. And then later in the course, we'll worry about how to get it to an initial speed. Same when it hits the ground. Obviously, it accelerates somehow to stop. We're not going to worry about that now. We'll worry about that later. Other questions? Let's go back then to our picture of what's going on. We have the ground. We have the ball that starts out 1.5 meters above the ground. We have the ball has a displacement delta x while I'm waiting to jump. So TD is my delay time, which is what I'm going to want to find. And then the ball keeps traveling with some additional displacement while I'm jumping, which I'll call T. This whole displacement takes place over a total time T plus TD. And then myself, I'm here at 2.5 meters. I don't do anything during TD. And then I have some displacement delta x. So this would be the player, and this would be the ball. Now, if I want to look at each of these individually, here is the ball. And as a vector diagram, what two pieces go into giving me the total displacement of the ball? What equation would I use to try and understand the total displacement of the ball? Someone's whispering it up there. I heard a whisper from over here. I have v naught t plus 1/2 at squared. Which direction is v naught? Which way is the ball thrown? Up. And which direction is 1/2 at squared? Down. So to get them to add from here and finish here, v naught t has to do that. And t in this case is t plus td. And then 1/2 at squared, 1/2 a t plus td does that. So this is my delta x equals v naught t plus 1/2 at squared. And that's for the ball. Any questions on what the ball is doing? Yeah.
Why do you have two sets of t?
Because remember, the ball is in the air while I'm waiting to jump, my delay time, which is what I want to find, and then it's also in the air while I'm actually jumping. And notice these two displacements are what are equal, because that's the time t and that's the same position. So this is my same position, same time. Now, for the person, it's the same thing, right? I jump, some total distance, delta xp, but I have a v naught t, we'll call it v sub p for the person, and I have a 1/2 at squared. Now it's just t because I do not jump during the delay. So for both of these cases, I have from my picture a delta x plus a 1/2 at squared equals a vpt. That's the sum of these two things is equal to that. Or the other way I can look at it, I can put the 1/2 at squared on the other side, and I have my minus sign, which I also could look at as if I picked up to be positive, then delta x and v are both up, so they're both positive, and a is down, so it is negative. And the one thing I know from my picture is that this whole thing equals that whole thing. So the equation, one of the ways I can do this is a number of different equations. Like I said, I could start from this height if I wanted. That would change things a little. But I write down 1.5 meters plus the initial velocity of the ball times t plus td minus my 1/2, and I'm going to call ag now because it is gravity, t plus td squared equals 2.5 meters plus the velocity of the player times t minus 1/2 gt squared. Now, what do I have in here? I know that, obviously. I know that. I know that. I know that. I know that. I want TD, but I need time. I don't know what that is. At this point, I go back to the question and ask myself, what in here, what facts have I not used yet? What in here will allow me to find the time t that I'm going to hit that ball at? The length of my jump. Right? T is how long I am in the air when I jump. At least in some sense. What fact in here is telling me that? How to find that number?
Your initial speed of 3.5.
Why is my initial speed telling me that?
Because you divide that by g to figure out the time.
Why?
Because that's how long it takes gravity to slow you down to stop.
Why do I care about stopping?
Because you have to hit it at the top of your jump.
And what happens at the top of my jump?
Your vertical component is 0.
Excellent. Okay, but notice how many questions that took. It was like, why? Huh? What? Where? Why? This is what's involved. What I say, solving a physics problem is breaking it into pieces. If you ask yourself the big question, you know, oh my gosh, time's not, I don't know how to get time. You will be stuck. If you stop and ask yourselves the little questions, you go, okay, what's physically going on? What did I not use? And you've kind of gone through it and checked all the physics. There's a key physics thing being said here. And the key physics thing is top of jump. We have not used that at any point yet. And we go back to our attempt to solve it. And we see, okay, we need a time. And what I've been told is top of jump. So I know that means the velocity of the player there is 0. And one thing I know about the motion is I know that the final velocity is the initial velocity plus a times time, which in this case is that velocity of the player. Let's call this velocity of player final. Is the velocity of the player initially minus g times time, because g was negative. And that initial velocity was the 3.5. So I know it's 3.5 meters per second minus my 10 meters per second squared times t, and that's going to have to equal 0. So the top of the jump is what's going to tell me how to find t. And again, this is one of those cases where it's going to be very hard to do this just by matching variables to equations, because there's lots of t's in the problem. There's lots of v's, there's lots of d's, there's lots of a's. Well, there's only one a. But there's two people moving, there's all sorts of things going on. So you really need to start your library of key words that tell you something about the physics. That's something you're going to want to do. Now, having done this, we now know t everywhere. And this can just become an algebra problem. We just have to work this out. It's a little messy because we've got the squareds here. And the algebra is a bit longer than what we've done. I'm not going to do it here, but I do want to highlight one thing. Notice it's t plus td squared. A common mistake in a problem like this is to write an equation that looks like this. Well, let's put the right minus sign in. So call this delta x for the ball of t, and then add to it v of the ball. Let's call this td and put the d's here. And add to it vt, vb of the ball plus t minus 1/2 gt squared, where this is delta x of the ball of t. Let's make that a little clearer. Why is this wrong? Well, no, but it does fly for 2 different times. It flies for the delay time plus the time I jump. And I have the 2 different times up there in the equation that's correct. What's wrong about saying, well, this is delta x. Delta x is x naught plus vt plus 1/2 at squared. And this is delta x. It's already in the air. It went that far. Now we just add vt minus 1/2 gt squared. And I've got my 2 delta x's and I add them. What is wrong about this way of doing it? Good to know what's wrong about this so you don't make the mistake. Yes?
Is it because you're, in the second problem, you're squaring them individually then adding them, and the first one you're adding them then squaring them?
So mathematically, it's the difference between squaring the sum and adding the squares. But physics-wise, what's wrong with this as a physics equation right over here?
I could be wrong, but isn't it like you're adding the displacement when like the total displacement is supposed to be just where it moved from like in one point to its final point? So you're adding it from like where it moved from its initial point to some point, and then like from some point to its final point, which wouldn't give you the same answer if you did it like all one way.
Essentially correct. And so why is this? If I did this correctly, though, I could do that. If I went from the initial, this goes from the initial point to where it is at TD. What is this doing? If I wanted to go from TD, where it ends up here, to its final point, what do I have to put here?
You would have to change you would have to put the displacement and a new initial speed of where it was when it left off the previous.
The main thing here is I need that new initial speed. I need the new initial velocity. The equation for displacement is the initial velocity at the time you want to start your displacement vector. So let's go back to our picture. I'll just redraw a new one. This is delta x of the ball for TD. That's delta x of the ball during t. And notice it starts at a new place. This point here has some new initial velocity of the ball. That is the velocity it has when it hits TD. So this displacement vector is that velocity times the time it's in the air minus the 1/2 gt squared. Not the velocity down here at 0. So it moves up, it not only displaces, it has a new speed, a new velocity. And it's this velocity that has to go there. And if you are able to do that, then you can add, because the picture says you can, right? I have this displacement plus this displacement does equal the total. So there's nothing wrong with adding that and that, as long as this one you calculate correctly with the right new initial velocity. And when I write it this way, I used this initial velocity, and that's the one that's wrong. So I wanted to highlight that. Any questions on that? This is the trouble with the more complicated problems. There's lots of places to make a physics mistake. And then at the end, you sometimes end up with a long algebra where you can make an algebra mistake. So if we look at that equation, you do a little bit of math, you will get something that looks a lot simpler. Oops. Now, what did I do here? For me, like I said, I like to plug in near the end. So I first got everything in the equation that had no TD, because that's what I'm trying to find. Then I got everything where it's just a linear TD, and then I had the squared. And now I see I have a quadratic equation. And we all remember the solution to a quadratic equation, right? TD equals negative b plus or minus square root b squared minus 4ac all over 2a. And I never learned it, and so I don't remember it. But like my daughter learned something about some b going to a party being negative, I don't know, and a square, and then meeting an a and a c. I don't, yeah. And it never seems to work. But there's apparently something you can do. But you do need, this is the, I'd say, trig and this you unfortunately need to memorize for your physics exams. But we have this is here. All of these are just numbers. So I can plug them all in. And it looks like this. You get 5 times TD squared minus 5.5 TD minus 0.925 meters. This equals 0. And notice there's a plus or minus here. So I get 2 times. I get minus 0.15 seconds. And I get 1.25 seconds. So as a clicker question, is our answer A, minus 1.5 seconds, B, 1.25 seconds, C, both? And, or I guess we can also go with D, neither. Excellent. Why do we know it's 1.25 seconds? What did the question ask? Did we forget already? See, that's what happens. You do the whole long problem. You forget what the question asked.
How long do you have to delay your jump?
How long do I have to delay my jump? Negative 1.5 seconds, negative 0.15 seconds is not delaying. That's jumping early. 1.25 seconds is delaying. Now, if the only answers came out negative, how long must I delay my jump? The answer to that is I can't delay my jump. If I want to do this, I have to jump early. So the answer might be I can't do it. That can happen. In this case, recall what we said on Wednesday, right? The ball is doing that. And I am doing that, reaching the top of my jump. So I can either hit the ball here when the ball is going up, or I can hit the ball here where the ball is going down. If the question said, when must I jump so that I hit the ball on the way up, what would you answer? Do you have enough information now to answer that? So yeah, let's vote for that one. When must I jump so that I hit the ball on the way up? And neither would mean you have to go solve for something else in this case, right? Let's take neither to mean I don't have enough information. Let's see how we did. Not quite as confident here. Half of you did think negative 0.15 seconds. Why did you think that? Yeah.
So you have to jump earlier so you get it because the ball's going faster than you.
You have to jump earlier so you can get it because the ball is going faster than you. Not necessarily convincing. Not unreasonable, but not necessarily convincing. First of all, why do we know we have enough information here? Shouldn't I have to solve for whether the ball's velocity is up or down to know which one is up or down?
Since the ball ball was moving up to begin with, you can assume the first time is when it's still moving up.
Exactly. We know how objects fly in the air. They don't suddenly go down, then up again. So the ball's going up first, then it's going down. So if I want to hit it, and there's two choices, an early time and a late time, which one gets it on the way up? The early one, because that's what it does first. So it's minus 0.15 seconds because I know up comes before down. Now, I might have said just that you delay 1.25 seconds and you jump and hit the ball at the top of your jump. And you did some work to solve the problem. Maybe I asked you then, is the ball going up or down? At that point, in that type of problem, would you necessarily have done it all this way, or would you have looked for something else? So let me write that down. Suppose we had pretty much all the information you were given, all the initial velocities, difference in heights, and I said, you hit the ball at the top of your jump with a delay of 1.25 seconds. Is the ball going up or down? Would you use probably the same set of equations, do the same calculation, find the minus 1.5 and the 1.25 and say that it's going down? Or would you probably do something else? Talk to the person next to you. Think about how would you do this one? Would you do that or something else? You had all the same information plus this. Okay. So let me ask you this. Turn this English phrase into a very, very short physics statement. If I was to draw this as a physics picture, what am I drawing? Somebody said it over here. It's a negative velocity. Ball going down is negative. Ball going up is positive. So this is about velocity. So fundamentally, I'm going to worry about the velocity of the ball. Its final velocity is whatever its initial is, minus g times the total time it's in the air, which is the delay time plus the flight time. And I've just been given the delay time, and I already knew how to get the flight time. How do I do that? How long am I in the air? I use what? What fact do I use? What physics fact am I going to use? My velocity is 0 in that direction because it's the top of my jump. So notice, do I ever have to worry about displacements for this question? No. So even though I were given some displacements, this is a case I don't need to know them. This is fundamentally all just about velocity. Much easier problem, much shorter mathematically. If you stay focused on what the different physics means. Ball going up or down, top of your jump, all have to do with velocity. So I'm also going to have a velocity of the person. Final equals 0, which is their initial, minus g times t. And now I've got my two equations. I've got everything I need, and I'm done. Any questions on that? Yes?
Is the velocity t the initial velocity of the ball?
Velocity t is, I don't know why I put a t down there. That's a good question. It's the velocity of the ball initial. I was probably just thinking ahead of myself. Other questions? Excellent. So we've now pretty much covered everything you need to know about moving in one dimension. And between discussion and what we've done in lecture, you should be able to do all the homework. As a reminder, at roughly 2:05, I'll be over in Roland Hall to answer questions on problems. What we're going to just do a brief, the way it's going to go, we're going to do the kinematics in 2 dimensions. I'm going to briefly review vector addition right now. On Monday and probably Wednesday, we have a bunch of demos as well as some example problems for next week of projectile motion. And then we'll be done with that. And you'll have your first exam the following Friday, which will cover these first 3 weeks. So the exam on the 26th only covers the first 3 weeks. It won't cover what we do on forces those 2 days before it. Clear? So vectors. Basically, the most common thing we have to do, as we saw, is add 2 vectors. We either had v naught plus at, or we had v naught t plus 1/2 at squared, equaling delta x. Very common thing to do. And if we have 2 vectors, a and b, we know that we've said we do the vector addition head to tail, tail to head, and draw the resultant. So, as a final clicker question, if that's a and b, which of the following is a plus b? Let's make it a little easier. So there's a and b. So one choice is that. I'm not drawing my b very well. You know what? It'll be easier. We'll make that b look like that b. There we go. We would do that. We can do that. And d is more than one picture is correct. There you go. Go ahead and vote. Most people went with B. There's some people going with more than one. That's one of the dangers. There isn't more than one. It's just B. Because the key features, I need head to tail. Right? This has tail to tail, so that's wrong and does not work. This one is minus B. It's in the opposite direction of B. So this one does not work. So the only one that's correct is this one. And then I've drawn it from the tail to the head. And that gives me A plus B equals C. Now, in kinematics, where this most often comes up, right, one of your vectors is G, which is always drawn that way. And sometimes it's G times time, which might be a little bit bigger, or it might be a little bit smaller if t is a fraction. And it's also 1/2 gt squared, which likewise can be bigger or smaller. Because when we multiply a vector by a number, it makes it bigger or smaller. And we're going to be adding that to something related to v naught. And so one of the very common pictures to have, and there's a really nice, I posted a PDF that reviews adding all of these vectors, but you're often launching something, so v naught is up. And then you can have a couple of different cases. You can have a time that has a gt squared like that, and that's your delta x. And notice you land some height above where you started, right? I could also have a 1/2 gt squared like that, where this is my delta x. And now I end up some height h below where I started. And then every now and then, you have the special case where you end up at the same height as where you started. And that's 1/2 gt squared. And in the given problem, you might be told where you land, so you might know whether it's above or below and be asked for t. You might be given t and asked you end up above or below or at the same height. Lots of different options as to what you can be given. One of the beauties of drawing your vector diagrams is you have lots of options of trig functions to use. If this is my angle that I'm given of my initial launch, I can say sine of theta is what? What's the sine of theta? Opposite over hypotenuse. Got to remember the great Princess Sokotoa. Sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. So the sine, notice the opposite is this. How long is the opposite side in this case? It's this whole length minus this length. So it's 1/2 gt squared minus h, and the hypotenuse is v naught t. Cosine theta is what? In this case, it's d, the adjacent, over v naught t. Tangent of theta is what? 1/2 gt squared minus h over d. Pythagorean's theorem tells me what? d squared plus 1/2 gt squared minus h squared equals v naught t squared. This is my a squared plus b squared equals c squared. Now in this case it looks kind of messy, but there are some situations that'll be easy. Notice you've got 1, 2, 3, 4 equations to choose from for your triangle, depending what you're given right off the bat. This is why I like drawing the picture, because it often helps you make a quick decision what equations to use. The other way to do all of these are components, right? We pick an x and a y, and if I have a vector A, I'll have the components in the x direction, if that's theta, of A cosine theta, and in the y direction of A sine theta. And I can get an equation for each component. So what I'm going to do is on Monday, we'll very briefly go over components. We do some demos, and we get started on some example problems. Good luck with the homework. Don't forget the quiz for Monday.